Hey guys, we're Group 1. Today we're going to talk to you guys about our concept for a thin-haul aircraft. And first, Yuya is going to talk about the big picture of our concept.
Hi everyone, my name is Yuya and I'm going to talk about definition of the problem. Here's a big picture of our project. And there are two main issues. One of them is small airports have been in high demand. However, no airplanes are available to it. And operating our project would cost really much. However, wouldn't profit much. And then those two problems lead to the demand of our project, thin-haul aircraft. And by doing thin-haul aircraft, we can benefit two things. One of them is the airline companies benefit more, and passengers can access to the rural area. Here are the stakeholders of our project. There are three stakeholders: domestic airline companies, and parts suppliers, and the passengers. Here are the needs, goals, and objectives. Our needs is operating our project should be by a single pilot, and it should accomplish short takeoff and landing distance. They should meet a low noise, and they must carry a designated payload for passengers in the bag. The goals: the airplane should have a high fuel efficiency, and it should be easy to maintain, and the maintenance costs should be lower. Objective: in order to design our aircraft, it should meet the requirement from small airport. Here's the concept of our operations that should meet our stakeholders' requirements. Here's another additional missions. This is the functional requirements. Here's the performance requirements. This is the constraints and verification requirements. Those three top-level requirements are explored later on slides. Here's the relevant examples of our thin-haul aircraft. One of them is Cessna 402. The other one is ThinHaul1 P2012. And this is a concept by NASA of our project thin-haul aircraft. It should be ready in 2025. And next, Ted is gonna explore decomposition.
Great, thanks Yuya. So up on the board, you can see the morphological matrix. You can see that we have a couple subsystems: the powertrain, the ECS, the flight control system, and navigation and landing gear. Some of these are subsystems, and then others are subsystems. So we explored a lot of options in order to make a decision on our aircraft. So up on the board, you can see the interfaces, and interfaces are really highly connected. You see a lot of data flowing throughout the systems, the different subsystems to the airplane, and out to different subsystems again. And you can see the powertrain is supplying the electricity for a lot of the subsystems. Here's our n-squared diagram. As you can see, it's really interconnected, which is great. Basically, the only two things that won't have a lot of connections are the pilot, but the pilot just inputs stuff into the airplane, and also the ECS, which supplies the fresh air into the interior. So here you can see the flow down of requirements. We chose 6 main subsystems to really focus on and write a lot of requirements on: the powertrain, the structures, the flight instruments, the ECS, interior, and the flight controls. So here are the requirements for the main airplane. These are pretty general. You can pause and read through them. A lot of FAA requirements and a lot of different requirements that are laid out in the AIAA request for proposal. So here are the requirements for our subsystem, the powertrain. Pretty general. It's based on a lot of different aircraft, just an offtake from the engine or something to allow to power the subsystems. And then some different requirements to allow for short landing and takeoff, and cruise requirements for our chosen Mach number of 0.4. Here are the requirements for the structures. It basically allows the airplane to allow for passengers, our propulsion system, as well as allowing for retractable landing gear. So here are flight control systems. This is pretty general. One interesting one is that in case of an emergency, our airplane needs to allow for only a 50%, the flight control system needs to work on 50% reduced power. Flight instruments, pretty general. A lot of these are already laid out by the FAA, so we have to conform to these. And then also just the use of GPS and then main flight instruments for the pilot. As for the interior, we chose to allow for 6 passengers, 1 pilot, so this is above the requirements laid out in the AIAA request. And then we also have different payloads allowed to be put into the airplane, and then a quick and easy boarding and deboarding process. Lastly is our ECS, and then these are pretty general for a lot of ECS systems, just a constant temperature in a range, constant flow rate, and then a pressure of 8,000 feet or less, since we are cruising above that, and we need to provide a pressurized cabin for our passengers. Next, I'd like to introduce Michael, who's going to talk about our 2 trade studies for our aircraft.
I'm just going to run through the trade studies we performed to help us choose which subsystem would be best. The main one we did would be for the powertrain. So we decided to do a trade study on the propulsion system because it will have a lot of effect on the success rate of our mission. The propulsion system is going to affect things like range and endurance of the aircraft. In addition, the propulsion system has a lot of effect on requirements and characteristics of our other subsystems. For instance, if we chose an all-electric propulsion system, we would not be able to use bleed air to power other subsystems. So for this trade study, we used a PU evaluation matrix, and we used a small turbofan engine as our data point. We compared a turboprop, a hybrid electric, turbo-electric, fully electric, and 2 internal combustion engines. And we evaluated all these off of safety, long-term operating cost, range, speed, turnaround time, emissions, and risk. At the end of it, we decided to go with the hybrid electric power plant because it provided a lot of improvements over the turbofan and other alternatives, as well as not a whole lot of downside. In addition to the trade study on the power supply, we also did a trade study on the automation. I won't go through too much details right now, but at the end of it, we decided to go with the automation system that's used in the DA40 because it had a lot of upside in comparison to other automation systems that are in similar aircraft. Up next, we have Jared, who's going to talk about our concept architecture.
So, drawing from our morphological matrix, our requirements and constraints, as well as our trade studies, we went ahead and came up with a concept architecture. So for our overall design, the aircraft is going to include 6 seats as well as the passenger. We are going to have a hybrid electric propulsion system as well as pretty standard features such as an engine bleed for the ECS, fly-by-wire control systems, aluminum structures, as well as many different pilot features such as an all-digital glass cockpit and a lightning detection system inside the plane. So now moving on to our more premium features, we are having a state-of-the-art propulsion system that's all hybrid electric. As mentioned, the pilot is going to have a glass cockpit, which is a very attractive feature, as well as really neat automation features that allow for that simple vehicular operation. We're also going to have interior design features such as spacious cabin seats and a pressurized cabin for the comfort. And so how do we compare with the rest of our competitors out there? As mentioned, we have a hybrid electric system for powertrain. As of right now, our other 2 competitors are an internal combustion engine or fully electric. And although a fully electric doesn't produce any CO2 emissions, you have to look at where the electricity comes from. And so as you can see from this graph right here, hybrid is the best choice for producing the least amount of CO2 emissions. As well, it also lowers the jet fuel cost because we're able to use electricity as well. And so lastly, for the pilot and the end user, it's a very comfortable aircraft as well as having that neat glass cockpit and digital features with the automation as well for simplified operations. All right, I'm going to go ahead and bring us over to Yash, who's going to talk about our verification steps.
Thanks, Jared. So next up, we're going to go over the methods we used to verify the requirements that we laid out earlier. So before we get to specifics, there's several ways in which you can verify our requirements. Some of them are simpler and can be verified just using simple physical checks or demonstrations. For others, we're going to use computerized analysis or simulations. And then finally, we get to more intensive full-scale testing. So first up, there are several requirements which can be checked just by physically inspecting the plane. For example, we have the limit on the maximum passenger load, we have provision of space for luggage, provision of necessary safety equipment, and so on. Next up, there are several requirements where before we actually get to more intensive and costly testing, we'd like to verify them using computerized analysis or simulations so that we can ensure they're being met at every stage. And for instance, you have the analysis of aerodynamic characteristics of our system and periodic cost and timeline analysis. Next up, there's other requirements where they can be shown that they've been met without needing to resort to full-scale testing with expensive equipment, and instead you can just do a demonstration. For example, we have a requirement about the time limit for loading and unloading, as well as demonstrating that the system can taxi to and from the gate without the need for a ground tug. And finally, we get to more intensive tests. So you have both ground-based testing as well as in-flight tests, and there are several pretty important tests that can be done on the ground. For instance, you have debris testing, including bird strike tests, stress testing, and simulated flight cycles to test the long-term durability of our aircraft. And then you have in-flight tests. So for this, you have two reference missions that were already laid out in the AIAA RFP for our project. And in addition to that, we've come up with some other tests, including a simulated engine failure, as well as ECS testing at high altitudes, and a test of our automated flight system while the airplane is in cruise. And lastly, we come to a life cycle of design and development that we've laid out for our aircraft. So up on the screen, you can see a screenshot of the Gantt chart that we came up with that lays out the entire design and production phases of our aircraft. And this was actually based on a similar NASA publication that went over the development cycle for a civil aircraft. And here we've assumed that design will begin immediately and the project will reach completion in the first quarter of 2025, which is well ahead of our requirement that the project should be completed by the end of 2025. And our aircraft should have an operation lifetime of 20 years before closeout of operations. So that brings us to the end of our presentation. Thank you for watching.